students, in the last lecture we have derived the formula for bandwidth and lower half power frequencies and upper half power frequency for series RLC circuit. On the basis of that, today we will solve a numerical and then we will study parallel resonance. First of all, solve a numerical. See, in a series RLC circuit, R is equals to 2 ohm, L equals to 2.0 millihenry and C is equals to 10 microfarad. So, we have to find the resonance frequency FR, quality factor, bandwidth and half power frequencies, that is F1, F2. In the previous lecture we have derived all the formulas. So, first of all write down the given value. What is the given value? That is R is equals to 2 ohm, L equals to 2.0 millihenry and C is equals to 10 microfarad. So, what is the unknown value? FR, that is resonance frequency FR. As you know, resonance frequency for series RLC circuit is 1 upon 2 pi root under LC, which we have derived earlier. This put the value of all LC, that is 1 upon 2 pi root under 1 upon L is 2 into 10 to the power minus 3 into 10 into 10 to the power minus 6. This much hertz. When you calculate this value, it is coming 1125.4 hertz. You can calculate this value. Now, next unknown value is quality factor, Q factor. What is the formula of that? We have derived that 1 upon R root under L upon C. Here you can put the all values R, L and C, that is 1 upon 2 root under 2 into 10 to the power minus 3 upon 10 into 10 to the power minus 6, and this value is coming after calculation is 7.07. As a quality factor, it is a factor, so it is a unitless quantity. Now next is your bandwidth. We have also derived the formula of bandwidth, that is R upon 2 pi L. You can easily put the value of R is equals to 2 ohm, 2 pi into 2 into 10 to the power minus 3. You can calculate this value and it is coming 159.55 hertz. Next is your half power frequency. There are two types of half power frequency. That is, what is that? F1 is your lower half power frequency and another is F2, that is higher half power frequency. So all these two formula I have derived earlier. One is your FR minus R upon 4 pi L. You can put the value FR is equals to FR is equals to 1125.4 minus R upon 2 pi L. We have calculated R upon 2 pi L, that is 1 upon 2 into 159.55. You can calculate this value and it is coming 1045.82 hertz. It is your lower half power frequency. Next is your higher half power frequency or upper half power frequency. It is also known as upper half power frequency is equals to Fr plus of R upon 4 pi L. We have calculated this value. Now Fr, put the value of Fr plus 1 upon 2 into 1 of R upon 2 pi L we have calculated, that is 159.55. You can calculate this value and it is coming 1204.98 Hertz. So all about this. On the basis of that, there is a so simple numerical which is coming in the university or any competitive examination. Now, next topic is your parallel resonance. Parallel resonance, we have a study earlier that the resistance and inductance is connected with the resistance and capacitance in parallel with a voltage source supply. So, what is the condition of resonance? There we have the conditions that in the series resonance, voltage across inductance is equals to voltage across capacitance. But in the parallel resonance, there will be a current, that is the sign component of current across RL is equals to sign component of current across RC. From phasor we can see that here is your V is your reference and IRL is your lagging with this voltage. Here is your lagging IRL and IRC is your leading with this voltage, that is IRC. It is leading with angle phi RC. So the component of IRC along y-axis is IRC sin phi RC and component of IRL along y-axis is IRL sin phi RL. So if these two components become equal, then current will be in phase with the supplied voltage. This is the condition for resonance. So these two components should be equal. That is, circuit will be in electrical resonance if IRL sin phi RL is equals to IRC sin phi RC. Now calculate all these value. IRL sin phi RC RL. IRL is what? IRL is, you can calculate V across this voltage across this IRL is V because it is in parallel upon impedance of this circuit IRL. We have written here V upon impedance R square plus omega RL square. Similarly, current sin phi RL can be calculated as impedance triangle. You can draw the impedance triangle of this, that is, here is your R, here is your XL and it will be your ZRL and it is your phi RL. So sine of this is R upon, sine of phi RL is equals to XL upon ZRL. We have written here, that is XL upon ZRL from impedance triangle. Put the value of ZRL. Now IRC, calculate this value IRC, that is voltage upon impedance of RC. IRC is equals to V upon ZRC. Put the value of ZRC. ZRC is equals to root under R square plus 1 upon omega RC ka whole square. We have written here omega R, that is resonance. At resonance, this condition I have been calculated. Now similarly sin phi RC we have calculated from impedance triangle, that is 1 upon omega RC upon ZRC. Put all these value in equation 1. We have written here and you can solve this value and simplify and find the value of omega R. So it is coming 1 upon root under LC, root under CR square minus L upon CR1 square minus L. So you can find frequency here, resonance frequency FR, that is 1 upon 2 pi and that value. Suppose that resistance across this capacitance branch is equals to 0, R1 should be 0. It can be there in the circuit diagram here. So put the value of R1 equals to 0, then FR is coming this, that is FR equals to 1 upon 2 pi root under 1 upon LC minus R square upon L square. Generally in the parallel circuit, R across capacitance is 0. So you have to learn this formula FR for parallel resonance. Suppose that across the resistance R1 is also, R is also 0. So resonance frequency becomes 1 upon 2 pi root under LC, that is series